Howdy. Come on, that was really bad. I know y'all are from A&M. Howdy. Howdy. There we go. That's more like it. All right. Up next, I want to present. Wait a minute.
That's what it seemed like. No, it's not this screen. That's way too much. It's just like chill out.
All right, howdy. Howdy. There we go. Next, I'd like to introduce Mr. Jason Brown from Micron to give his keynote speech.
So my bio was up there, and you'll see I'm a circuit designer. And after my presentation, you'll realize I'm a circuit designer. I'm not a presenter. So I hope to not thoroughly embarrass myself there. So my topic is engineering and AI's future circuits. When I think about artificial intelligence in the future, I oscillate between excitement and concern. I get very excited about the what it's going to enable in our world, the changes it's going to make to every aspect of society. But I'm also concerned about the possible impacts to humanity. That's, and being a design engineer, I'm also intrigued by the technology we're going to need to enable AI to reach its full potential. So I geared this talk into two parts. The first part, I talked about the technology behind AI, mostly focusing on memory systems. And the second part, I talk about possible consequences, and maybe I try to give some advice to engineers on how to navigate a world of AI in their career. So I guess I should talk about Micron since they paid for me to be here. So Micron, we make semiconductor memory. We make the fourth most silicon in the world. I know most of y'all probably haven't heard of them, but we're based in Boise, Idaho. We have fabs all over the world. We just recently got a big CHIPS grant money to build a $20 billion fab in Boise, Idaho. We're also building 5 fabs in New York. They're going to cost about $100 billion. So we're spending a lot of money to bring manufacturing back to the U.S. I'll say one more thing. Micron is a end-to-end company. We're not fabless. Most companies today don't run their own fabs and design their own circuits, but we do everything from packaging, design, develop new technology. So that's enough about Micron. That's not very interesting. So here's the definitions. I've been in here, so I'll talk about these today. You know, on the slide deck, you can go over them. So somebody once told me to start the presentation with a joke, so that's what I did. And this is a joke written by a human, and I'll let you read it. It's not falling or shit funny, but at least there's some humor here. And there's the incongruity between caveman and AI. It's kind of humorous. Then I asked AI to write a joke. You can see that says, why did the AI go to school? Because it wanted to improve its algorithms to become a smart machine. And good, nobody's laughing because that's not funny. They did the emoji there to make me laugh, but so I did this slide to at least say cartoonists are safe from AI for a few more years because they don't have very good sense of humor. So, bad joke aside, I do think we're reaching an unprecedented era of artificial intelligence. And the reason why I'll try to explain is look at the number of years it took to get 50 million users for different technology. It took airlines 68 years to get to 50 million users. Other technologies here you can see, but the number of months it took ChatGPT to get to 100 million users was only 2 months. And it's a digital age, so everybody gets that. Information spreads rapidly. That's why there's concern, because it's going to spread. Something good is going to spread rapidly. So if you look at this, I tried to define something called transformation velocity. That's impact on humanity over speed of adoption. And let's look at some of the biggest inventions throughout history. The wheel, big impact, but took 500 years to spread. And this is all very subjective if you're scientific formula for all this. So, but if you look at AI, its impact is going to be tremendous. It's going to spread so rapidly. So its transformation velocity is the highest of all these inventions, possible highest. Like I said, it's very subjective, but that's why I think it's unprecedented. And why does Micron care? I want to read that real quick. So several people, I think Robbie talked about this earlier, the data center. This is data center capital expenditure. So this is mostly the big companies spending this money, like Microsoft, Meta, AWS. And this year, we're going to spend about $500 billion on CapEx for just building data centers. And $70 billion of that is memory. In 2028, it's going to be close to $1 trillion it's going to be spent, and $170 billion of that's memory. And half of that's going to be probably the memory that my team makes. There's a few people here from A&M, Matthew and Thomas Dawson, they're from our team. We design high bandwidth memory. So there's only 3 companies in the world that make high bandwidth memory. So we'll get 40% of that memory. So $50–60 billion of revenues into the high bandwidth memory in 2028. So the rise of Gen AI, this I thought was interesting here. Somebody earlier brought up AlexNet. So this is the computational requirements of training AI. And AlexNet was kind of, everybody recognizes that as the first language model. It was used for image recognition. It was amazing what they came up with. But that only took 10 to the third petaflops to train. And you can see it escalated about a pretty low rate, like 8x every 2 years for the first 5 or 6 years. But with the onslaught of transformers, which are the large language models and used in generative AI, huge billions of tokens, the number of petaflops required to train started escalating rapidly, 8x every 2 years. So that means the compute has to keep up. If you look at compute, you see, somebody talked earlier about CPUs. CPUs are amazing, but they can do everything. They're multifunctional. Jensen Huang recognized early that GPUs would be great for AI training. So that's NVIDIA's CEO, by the way. If you ever get a chance to watch his videos, he's an amazing presenter. It's just, you learn so much from him. But you can see GPUs, their computing performance is accelerating rapidly. It really can train them to do what is needed for large language model training. So the performance has gone up 1,000x in 10 years. So that's memory has to keep up with that. So that's what we've been working on. So let's go through real quick the 4 types of AI. I'll be quick with this. Perception AI, that's AlexNet. That's sensory. It's recognizing images, sounds. They even have some that recognize smell and taste. That's starting. Generative AI is the one that everybody knows about. That's ChatGPT, that's Grok, that's Gemini, Copilot. Those are the huge ones that are using hundreds of billions of tokens to train. And then agentic AI, that was mentioned earlier. That's more of your more domain specific. Like you have that in your car, a very simple version. Google Maps, you get your car, it says it's 5 o'clock, time to go home, here's your best route home. That's a simple agentic AI. And physical AI is the exciting one. I think Benjamin mentioned digital twins. That's part of that. Digital twins are replications of factories in the digital world. It's also robots. It's also self-driving cars. And the thing about this is interesting. I use a laser pointer, but the amount of data needed by all these is billions, and all that needs to be on memory very close to the CPU. So let's look at Grok for a second. So I got props here to make this more interesting. So Grok was built by Elon Musk. So this is a you mentioned this is a H200. This is a Grace Hopper. This is a brand new one actually. It's worth $35,000, so it's very expensive. And it's got the Hopper GPU there, and surrounded it 60 feet of memory. So this was trained. It's actually newer version of the one Grok was trained with, and it's Grok was trained by 100,000 of these GPUs. And it ran for 8 days straight. Each one of these is capable of 1.4 times 10 to the 15 flops. So training Grok took around 4 times 10 to the 26 flops. And the energy required to do that is 175,000 megawatt hours. That's the amount of energy you can use to power 50,000 population city for 3 months. That's sad. Maybe not Texas in the summer 3 months, but a normal city for 3 months. So somebody asked about sustainability earlier. Work on power for semiconductors, and you really impact the world. So I want to put this number in perspective. It's a staggering number. 4 times 10 to the 26. If you take every person that's ever existed on the face of the earth and counted the number of words they've spoken in their lifetime, and added it up, that'd be 7.7 times 618 rows. So, the number of flops to create grok equates to 60 million operations on every word that's ever been spoken. So to create a neural network or a brain, that's how much work it takes. And that's what grok thought it looked like. So I asked it to create an image of itself, and that's what it gave me some. So let's talk about the demands of AI infrastructure and how memory is involved with that. So performance, like I said before, large language models need tremendous bandwidth. And right now, they don't operate at peak performance because the memory can't keep up. They're operating less than 50%. Capacity, the models are growing bigger and bigger. So we need more and more memory we did to help them operate. And then power. Somebody else quoted this earlier. Right now, data centers consume 3% of the world's electricity, and that's going to reach 8% by 2030. That's shocking, especially since so much just wasted on stupid things like Netflix and cat videos and put on. So I want to talk about what we do real quick. This is what we make in Micron, and this is a GPU here. This is like Hopper or Blackwell is the newest one. And we built what's called a high bandwidth memory. So we stack up 8, 12, or 16 DRAM chips on top of a logic chip at the bottom that then communicates through an interposer over to the GPU. And you can see it. So I showed just one, but usually it's like this. All these pictures, everybody showed a bunch of pictures today of NVIDIA's chips, and every one of them you can see the high bandwidth memory sitting right by the GPU. And these are through silicon vias. These are amazing. These are basically holes in your silicon so you can stack things on top, and instead of going like in a left to right nature on a chip, you can go in a vertical direction. So we have hundreds of thousands of TSVs on these chips to communicate information and deliver power. So this is very interesting, and this goes right into Cadence's role here. So this shows NVIDIA's B200, that's the Blackwell Grace chip. And the interesting about this is look at the size of this. You can't tell here, obviously, but this is so large you can't print it. It's bigger than a reticle field. Reticle field is 26 by 33 millimeters. This is 2 of those. It fills up the entire reticle field. They fit together, and they have to communicate through an interposer. So it's grown that large. And then, but everybody doesn't want to pay NVIDIA $35,000 for 100,000 of those. So everybody's getting into it. AMD is starting their own design. Broadcom. There's several other companies, SoftBank. Our team at Micron talks to these companies every week. Because they all have the little magic they're trying to put into the HBM. They want custom solutions now. So it's becoming a very exciting world for memory, which forever was the most boring thing in the world. So here's another interesting slide. So this is a picture of, I stole this from Jensen. He was at GTC 2025 2 weeks ago. This shows a 300 millimeter wafer, and it shows all the silicon on that wafer that's needed for the NVIDIA Grace Blackwell. So it's static. So this is a 300 millimeter wafer right here. Imagine printing one chip on this entire wafer. And there's no way you can do that. And the reason why is you need totally different technology to make DRAM die versus making GPUs. It's completely different. You can't do them in the same bag. And just to see what's on this die, there's 72 Blackwell GPUs, 2,600 CPUs, 576 memory cubes. This is all the memory here. And like I said, this is just a cartoon. And all of this goes into this stack right here. And actually, this is just a snapshot I took on YouTube. 5 minutes? Oh my gosh. There's 130 trillion transistors on this. And so what is enabling these systems? We'll do this real quick. Heterogeneous integration. that was mentioned before. It's a method of combining different types of components, materials, and technology into a single system or subsystem. And this is new. I mean, it's been around for a while, but this is the exciting thing that's going on now. So if you look at HBMQ, you have Micron's process on here. At the bottom, we have TSMC's process for this logic die. This is like 12 nanometers, we're going to 3 nanometers in some of our new designs. So then we have to integrate those together with amazing packaging. So this shows some of the problems that we have to solve. There's TSV blockages. Like I said, there's holes. So you have to build your logic knowing there's going to be 100,000 holes all over your die. So that's something. Power delivery. This is the hottest part of the die. It's the very bottom of that stack. So somehow you have to have low thermal resistance at the stack to get the power off to the cold plate. Next slide. Chip package interaction. So this is a very exciting field that used to not even exist. Like I said before, if you think about the stack here, there's 150 metal layers in here. If you think about a whole 16 high stack, there's over 1 million TSVs. And then it sits on top of these 1,000 micro bumps at the bottom. And there's a lot of mechanical stress on the design. So we have to create packages to send out to our customers a year in advance. And we have a year cycle between each iteration of HBM. So it's extremely challenging to make this work. So what's next for HBM? This just shows the system requirements are going to keep going up. Memory's not going to keep up, so you've got to come up with new technology. Same as power. Power's going to want to go down. Memory's not going to keep up. You've got to keep doing new technology. So you have the better TSV scaling. You have to implement hybrid bonding. We need better CMOS, better metal. So this is a cool chart. It shows the amount of power, or the number of calculations you can do per 1 watt. And it was 3.2 gigaflops per watt. Now it's up to, someday we'll get to this. The reason I bring this up is, your brain is 500,000 gigaflops per watt. That's how efficient it is. It's 2,000 or 250 times more powerful or more efficient than we ever will get with a GPU. So you are all blessed with an incredible intelligence, not artificial intelligence. So let's get to consequences real quick. This is what I'm talking about. Worry about AI and what's going to cause. So you might recognize this quote. His name is actually brought up sooner. It's actually, he's talking about John F. Kennedy. He's talking about the space race. And the reason I bring it up is, this picture's kind of scary, is the novelty of the situation isn't new. Throughout history, we've been scared of technology and what's coming. In the 40s and 30s, there was nuclear power, nuclear bombs. There was a space race with the Soviet Union. So I know it's intimidating thinking about AI replacing everybody, but people have always been scared of that. So job displacement, I want to talk about that for a second. These are all the predictions about job replacement. I won't read them. So, and then I asked Rock, when will these jobs be replaced? Of course it had all these dire projections. But I want to show you this real quick. Doctors, I don't believe, doctors, the training's going to need to change. They're not going to rely on memorization. Because why do they memorize thousands of cases and bones and everything else? But it's all right there at touch of a button. And the improvement in medicine is going to be a tremendous positive impact. We're going to have enhanced diagnostics. A child in a village in Africa get the same treatment as somebody at Johns Hopkins with the best doctors in the world. Well, personalized treatment, somebody talked about that earlier, new drug discovery, predictive analysis. Somebody mentioned somebody wanted to know if they have diabetes or cancer. Let's tell you, teachers, similar to doctors, the training emphasis will need to change. And I don't envy teachers and professors, especially how do you design assignments when everything can be done by asking a simple question from a computer. But it's going to change the world, I think. AI tutoring did a study in Nigeria where they did in 6 weeks with an AI tutor for students, they achieved it only takes 2 years. That's amazing. And the ability to learn any subject. Imagine somebody who lives in the north slope of Alaska and can learn semiconductor physics with a great AI tutor. accountants and lawyers, nobody likes them, but I want to say here, software has had major impacts before, Excel and Westlaw, and they navigated. Their careers are going to change, but it's not going to eliminate them. There will be inflection points, but they've navigated. And then the creative industry. What I think is going to happen here, you guys know this, is the winners will be those who use tools to amplify their vision. So it's like getting a fancier version. I don't even know any artistic tools, but AI does give the illusion of creativity, but at light speed, but it's not true creativity. It needs somebody behind it. And the programmers are already being impacted, but software challenges are just going to keep growing. So emphasize domain expertise and high-level problem solving. You're just getting just more abstraction. Somebody mentioned earlier programming assembly outside of me, somebody did. And all it is went from machine language to assembly to COBOL to C++ to whatever. And now it's just another level up. So this is my last slide. Shows the father of electrical engineering. Engineers are problem solvers. AI, go engineers. To be honest, I don't think engineers have to worry about AI. Embrace the technology. Use AI every day. I use it every day. I use it all the time. And its transformation velocity will create a lot of opportunities. But don't just use it to make your life easier. Don't do it to answer your homework. Use it to show you 2 different ways to solve your homework problem. Work on your communication skills. This is very important. When presenting the story you want to tell, when answering questions, understand the perspective of the person asking the question. Don't get the same answer to your grandmother that you give to your professor. Know how to adjust your answer depending on who you're talking to. And understand what is needed for each situation. You need a fast answer or backup envelope calculation. Or you need to be thorough. You need different answers at different times. Don't get bogged down. When somebody asks you for something, spend a month on it, and they really just wanted a 5-minute answer. And this is the most important. Stay curious and passionate. Don't be afraid. As mentioned earlier by Matt, fail fast, but you just told me today, succeed fast. That's great. So that's all. Thank you, everybody.
Howdy. Thank you, Mr. Brown, for that keynote speech. Up next, we have our panel, but before we do that, I'd like to announce again, for those who have joined us just now, thank you for being here. If you haven't already been told, our event guide can be found on our website, and that'll show you the list of the programs, who's speaking at what time, and when the breaks are. So for those of you that are new, please check that out. Additionally, we will not be having a Q&A for Mr. Brown because we have our panel coming next, so please, kindly, I ask that you save your questions for that panel while our guys are getting set up. Thank you.
Howdy. I'm Akshat Nerala. I'm the president of IEEE here at XAN. I'm class 45, so I'm graduating next month. So as my friend set up the panel, I'd like to take time and introduce the panel. So we have highly specialized industry professionals. We're also a company that is today with us. We're honored to have you guys here. Start off with Susan Brown from Orange, Angelo Sanchez from Texas Instruments, and Jason Brown, who just gave her a keynote from Micron, Benjamin Salmo from Cadence, and Christian Rees from Insight Technologies. Let's welcome our speaker. And we also have Davos, who's our moderator today. He's an assistant department head for us, associate department head, my job. Thank you, Stavros, for moderating this panel too. Let's welcome Stavros with a big round of applause.
Howdy.
Howdy. Okay, you're kind of almost there. I guess you're still sleeping from lunch. Okay, well, we'll move ahead with this panel to try and stay on track. Almost looks like this one's going to pull down, but panelists, thank you for joining the panel. So what I'm going to do first, I'm going to ask you a question. You all respond to the same question. Before you respond, please introduce yourselves and just give a soundbite with respect to that question. So if you needed to repeat the question, when it gets to you, let me know. So here's the question. For students that are new to the industry, can you briefly explain where your company fits into the semiconductor value chain? We'll start with Susan and go all the way around.
Hello, I'm Susan Graham, and I work for ARM. So, at ARM is a British company, and where we are in the industry, there are two computer architectures in the world, and we are the most pervasive as far as risk versus risk. And so we're in a low power architecture. And we're considered more of IP, and we're the most part collaborate across the ecosystem. Qualcomm, Apple, everything that you would be able to provide.
Hey, my name is Angelo Sanchez. I am Field Quality Director for Texas Instruments. So I deal with a lot of companies, some of which are here actually. I was just saying that I deal with Micron often. So where does CI fit in? We're an analog semiconductor supplier. We also do embedded products as well. So we use ARM processors in some of our embedded product lines. I will say that our emphasis today is on bringing manufacturing back to the U.S. and we are working actively on developing several new fabs, not only in Texas but also out in Utah. And so I see a huge future in analog semiconductors, MCUs, and digital semiconductors as well. And I think that the application spaces that we get into continue to expand every year, and the number of electronics components in every application expands every year too. So a lot of opportunity ahead.
I'm Jason Brown. I just talked, but I'm from Micron Technology, and where we fit is, like I said before, we're the entire chain. I mean, that's why during COVID, memory was never in short supply, because we did everything ourselves. Other things, you had to rely on somebody else. The only thing we couldn't do is build things. We needed to supplies to build things, but that's what's interesting about Micron, I think, is you can move around and be in every aspect of semiconductor design and manufacturing.
All right, and I'm Benjamin Sarko from Cadence Design Systems, part of the Cadence network, so we connect universities. So where does Cadence fit in the value chain? To design these semiconductor devices, one of your EA seller, depending on how you count this. So what does EDA does? Right? It's really getting all for your inputs, what you want to design, making sure that we are building into the specifications of the factory we're going to, and then send it off to that factory. Simplicity. That also includes our design, evaluation,
Thank you. Christian Reyes from Keysight Technologies, partner account manager. The way Keysight fits into the value chain is really across the board as well. What we're trying to do, our design philosophy, is to really virtualize the prototype at the inception. And by doing that, you create a model. And that model you're simulating so that we have a data set for that simulation. And so with that, how do you communicate that to your test instruments so that it's automatically configured hardware there? So now you're able to emulate those same signals. measure those verification tests and validation tests. You have a separate set of data sets that can feed back to that virtual model. Now you can do a comparison that optimizes your design for manufacturing. So we're trying to make it as seamless as possible by providing those tools to engineers by integrating hardware and software in our instruments.
Word. I was going to say that word, but we didn't have feedback. That's good. So we turn it on. Okay, so I'm going to ask more targeted questions from each one of you right now. So the first one is for Angela. What are the key technological advancements shaping the future of semiconductors?
So I'm going to give a little bit of a biased answer just because I am in quality. So where I see technology going, or the key challenges for technology, again, are going back to these expanding application spaces. And if I look at a vehicle, a car that you drive 15 years ago, you had maybe 100 to 1,000 semiconductor devices in a vehicle. Today, you have tens of thousands to hundreds of thousands. And so with that in mind, I think that we are approaching spaces where we have to think about quality and reliability differently, and how we can ensure safe applications for safety critical applications like vehicles or like the space program, or even in the high-end server market, right? You mentioned AWS earlier, or Meta. Those servers, if they have any downtime, can cost the company millions of dollars very quickly. And so we're seeing just a complete change in the landscape from a quality perspective on what's required for semiconductors. And so I think we've got an interesting path forward on how to be successful in that space. I think it's going to take a lot of innovation and new ideas from companies, not only TI, but our end customers, and also from the industry as a whole, JDEC and other industry specification type of representatives.
And this one, we line this one up for Benjamin. How is AI influencing semiconductor design, manufacturing, and commercialization?
All right. I think as I said earlier, it's taking off. No, it's, I think, you know, as I mentioned through my talk, what AI is bringing to the table is really the ability to be efficient. It's bringing a lot of efficiency capabilities to the table. But it's also allowing us to really think even broader. Right? There are times where you thought of, you know, I'm going to create this new design, but it's going to take so much time to do it, right? And that kind of dissuaded folks from creating that next thing. But today, with a lot of the AI tools and AI capabilities, we're able to think broadly. Where I actually see some direct impact is the ability to take what is happening in the real world and feed in labs. Right? I thought about shift labs, where we're trying to do everything in simulation. Right? I think the earlier we can see where problems are, the better we are in designing our lives. Right? And so if we can actually take real world information and feed it back into how we design it, that actually makes you become a better design. And I think that's what AI can do. Right? Angula's quality, right? If I'm looking at a certain design, and that design is consistently having certain failure modes in the field, today it takes a human to say, oh, okay, I think this part, when it's run at -40 in Shanghai every year, all the cars locked don't open, right? Something like those things. Right? But are there certain things, certain characteristics of that particular device in that particular region that I can feed back to my products today? Right? Today it takes a human to do that. I think where AI can really help is crawling all our data sets and looking at where there are nuanced differences, right? And trying to feed that back into it. So lots of areas that we can see advantages of AI.
We're doing exactly that in quality at TI today, is AI and machine learning to detect small signals.
Good. Next question. What are the biggest challenges in taking semiconductor research from the lab to large-scale manufacturing? And this one is for Jason.
I guess in my field, it's to do stuff to create a reproducibility in the lab, you can do anything once, but we have to be able to do it 100 million times. That's what I see. We see a lot of great ideas come and then they don't pan out. I wish I had a better answer to that, but I think that's what I've seen. Yeah, that's probably about all I had. It's just, schools are great at ideas, but the viability of them are not there. Like the space presentation this morning, that's amazing stuff, but it's just how much money it's gonna cost to get that to a level where it can be monetized and be profitable. And it's sad to say that's all companies care about is making things profitable. So we still need the university research. It's just, we need a proper balance of money-making ideas versus just deep research.
Thank you. For Susan, what are the most in-demand skills in the semiconductor industry today? What are the most in-demand skills?
That's a hard question. I'm gonna bring it back, and I want to be more relatable. I do spend a lot of time recruiting. And this year's March, the first year, I started a new job, and I hired 2 college grads right out of school. In fact, I picked them off on campus. And what I tell them is what I need them to do is to think. You're engineers, you solve problems. Engineers are compulsive problem solvers. You've been at an airport and you see someone walk in and they're like, hey, this line and how they constructed this sucks. I can do it better. You're an engineer because you sit there and you recognize a problem, you're annoyed with it, and you want to fix it. That is the skill that you are here for. So where you apply it is really where you follow the money. So the other part I would say that my talent that is needing is a little bit of humility. We've been really successful, and if you look at the history of semiconductors, manufacturing, everything you guys are talking about has scaled in process technology. The complexity of it and how we got there has been my lived experience, and it's been a privilege to see. And applying that same principle of reproducibility and predictability is what manufacturing is. And Moore's Law has always been about cost efficiency. It has never been about transistors. It's like how much money I can make. So the other skill that I tell my new grads what they need to do is, in that humility, also have a level of confidence. And I tell them they come into my team to challenge us. If someone who's been here 30 years can explain to you why we're doing something, then they don't know what they're talking about. And at some level, they're threatened by it. So you need to be respectful and say, hey, could we do it this way? And I challenge them to help us with those new ideas. So where we're at is that we need to scale. I have to convert my OGs into younger at the point, which is scaling the way we attack problems. Instead of saying in my head, I can conceptualize 3 or 4 solutions, we have to let the computers do it, because they are simply smarter than we are. We built them to be that way. And it's still a very methodical way that you're approaching that you've already learned and practiced in your pursuit of education. So it's about confidence, humility, and compulsive problem solving.
Great answer. For Christian, how do companies decide which new technologies or research areas to invest in?
Yeah, it's a great question. So that touches on one other philosophical point that Keysight likes to implement, and that is every year we take 16% of our gross margin profit and we reinvest that back into R&D. So we're a big proponent of innovation, being at the edge of technology development. And the way we implement that is we actually employ, I believe it's 5 or 6 research fellows within our company. All of them from the original company of HP, which is where Keysight came from. And from there, we actually listen to our clients as well. So that's partly my job. So I sit down with our top clients and we look at their test plans or their test flows, and we offer consultation on that. And if there's any point of their technical requirement that is novel or unique, or maybe we don't have a solution for it at the moment, it's my job to correspond that to our research fellows. And then we'll do a deeper dive market analysis and investigation on that new requirement. So in that sense, we're looking at the broader market trend when it comes to investment. So definitely we're investing in AI, the electric vehicle, alternative energy, even academia or education is a big part of our goals as a company. But then we also look at the micro level as well. And so how to create new test instruments and systems to actually bring to vision exactly what I described earlier. Hope that helps.
Thank you, Christian. Susan wants to go again, so I'm going to ask her a question. What role do semiconductor startups play in driving innovation, and how do they interact with established players?
I believe there's startups within companies, just like with research. So when I say startups, I would say it's trying to do things differently. And I would say that in my role, I think in semiconductors it's needed. It's almost like you need some level of coverage of what you think you should be investing in as far as what is that turnaround and what the market and all of the smart people in the market tells you want. And the startups allow us to kind of go into that fidelity. As you scale and what we're doing, it takes a lot of details to get there. This is hard. But then at the same time, you have to zoom out to see how it connects. Because usually in those connect points are where we lose most of the goodness. And being able to recognize it there. So startups allow you to drill deep and kind of have that kind of focus that is required to solve complex problems, as well as they are allowed people to do more risk taking, so that you don't have to spend 6% of your revenue on a new idea, and you can spend your full time.
Jason, with more laws slowing down, that has been happening for a few years, what are the emerging technologies that will define the next era of semiconductor innovation?
I touched on that briefly, and you're right, Moore's Law is coming to a stop. And I heard that Moore actually predicted heterogeneous integration. That is amazing. It might be that insightful to know that at some point you're going to get as many transistors as you can into X, Y dimension, and then you're going to have to start stacking. So that it's the packaging technology that's got to keep improving, and it's got to be able to handle different types of materials interacting with each other that heat and cool at different rates. So ways to analyze that in the digital world, so you can analyze it quickly and then adjust how you manufacture your parts. I'm trying to think of any other things I can think of. That's probably about all I have right now. I mean, we're going to go to 2.5D packaging right now. Then we're going to 3D packaging. We need some way of cooling. That's the road that we're running into. And better methods of liquid cooling. I guess I am not involved with that at all, but that's always going to be a issue. Every watt you spend on compute, you spend a lot on cooling. And it's probably even worse these days because we're more efficient at the computing part of it, but cooling, we got to figure you out. So, thank you.
Thank you, Jamie. Angela, what role do interdisciplinary skills, like software, AI, and supply chain, play in shaping the future of semiconductor workforce?
I would say in every way, right? I mean, hardware doesn't do anything without software. And so if you don't have a strong software infrastructure around your hardware, then your hardware is useless. And so I think it all comes into full effect, right? At TI, we hire mechanical engineers, computer engineers, electrical engineers, chemical engineers, and you need that interdisciplinary focus to be successful as a company. And even our customers require the same kind of interdisciplinary exposure or experience and makeup of their company. So I think it's 100%, you can't survive without that. Essential.
Benjamin, what advice would you give to students today as they're transitioning from being at the university in this cut and paste rubric environment to to industry, be it either coming from research or for undergraduate?
It's a very, very good question. And what somebody would say is, industry is very different from academia and so on and so forth. Yeah, the answer is actually yes. The homeworks are, not just work at A, they work at the bottom of the company. So I think it's kind of starts from that perspective. But I think one advice I'll give is you're being given a set of educational principles, a set of educational tools. How you apply them is when you get into industry. So I learned electrical engineering, great. But you go to work for a company, the that idea or that problem solving technique or that fundamental that you learned, it's now time for you to apply it, and you apply it broadly. So, I worked at TM for a long time, right? And we interviewed a lot. When you came in for an interview, one of the questions we asked a lot is what is home stuff? And you kind of expound from those. Why are they asking us so fundamental, high school kind of question? But how current and voltage and resistance are related, this is practically our business, right? And we get complicated after that, right? And so understanding what that is and how you apply it in the function that you're in, it's the most important thing. So my advice is really look at how you apply the learning that you've taken or the learning that you've gained into the workspace that you're going to get. Right? So whether you're a designer, test engineer, software engineer, whatever it may be, right? That fundamentals, you have the fundamentals. Believe in that. Is how I apply.
Christian, a lot of stuff going on around the world today. We're not going to spend time in politics. But the question is, how are semiconductor companies adapting to the geopolitical challenges that are likely to disrupt, if not disrupting already, the supply chain?
Yeah, that's a
The
little
market, by the way, is solid red today if you haven't seen it.
Oh, great. Yeah, so I'm not too involved in those business decisions, but it is affecting us at every level of the organization. So, for example, Keysight has a fab in Santa Rosa, California, Colorado Springs. We develop our own proprietary ASIC chips for our RF products and our oscilloscope products, or time-based products. But our main manufacturing assembly hub is in Malaysia, Penang. So we're definitely going to get affected by the tariffs that have been implemented recently. And right now, management is really taking a step of, setting up contingency plans, but they're on the fence right now from implementing some of those plans because they want to see what is the long-term implications and if there are any changes that are coming down the pipeline in the next few days. So yeah, definitely going to be a disruptor in our business, but I think we're prepared, we're ready to adapt. And frankly, I think that's one of the qualities that a student should have when they're starting their career is adaptability. I was actually moderating a panel at South by Southwest a couple of weeks ago, and one of our panelists was the senior engineer from Starlink. And I turned to him and I said, can you share with us, some of the elements of agile development that you implement in your testing plans and your test flow? And he looked at me and he did not hesitate. He didn't even blink. And he said, oh, no, we don't implement agile. We do something that we call chaos. I'm like, what? It was such entertaining and humorous response, but there's some truth to that. And the truth is the ability to be adaptable. This is not be afraid. You're going to have this continuous integration, continuous development that is agile. You're not going to be thinking about agile when you're implementing your test plan or your test flow. So definitely adaptability, I think, crosses, it really transcends between business and engineering in this case.
Very good. So I'm going to ask you some questions now, and each one of you gives me their answer for these specific questions, right? The first one here. With the rise in U.S. semiconductor investments, right? So this is the CHIPS Act, and also the very famous impact that it's going to have on international trade. How do you see the industry landscape changing for young professionals?
I think the future is bright, and that's not to kind of, right, I mean, from my perspective, right, for to be coming out of an engineering background or an engineering education, there's a lot of, it spans the breadth from either hardware engineering all the way to product or financial engineering. But I think today, especially in the semiconductor industry, semiconductor is driving predominantly a lot of the advances in technology, whether it's finance or medical, whether it's automotive or factory automation. A lot of it is being driven by semiconductor, and you have that skill set. And so with the investments happening here, that means you don't have to go far, right, to participate. But you should also remember, knowledge is not only captured in the US. Knowledge is everywhere, and everybody else can be equally as smart. So taking that as perspective, which means you cannot take all these investments here for granted. Right? We have to take advantage of it. Right? We have to ensure that we are producing the right students, or we are also producing the right devices, the right technology, right? That would be our value. So I think, yes, the future is bright. I think there's a lot of opportunity when we say growth opportunity by funds and so forth and so on, right? But it also says, you know, always have a look in the review, because there are others who are also very interested in that.
So, I had a great answer, but I forgot it, but,
That's my class.
yeah, you talked too long. You know, the one thing I am seeing that's kind of, I don't even know if I should say it out loud, but we're moving the manufacturing back to the US, and that happens without a doubt. But I see a lot of the design and development is being moved overseas. So that's because you can't put the tariff on knowledge, and that's, so companies are always gonna try to save money, and they're saving money by moving design, R&D to cheaper areas. So that's one thing I see going on right now, and it hasn't, I'm sure TI, you probably seen the same thing. So it's occurring, so I'm kind of concerned with that, because we can't lose the brain power. We have the greatest brains in the world come to the US now. I mean, all the H-1B visas from India are amazing. That's what they drive our industry. And we need that to keep occurring, or we're gonna be in a lot of trouble. So I hope that trend doesn't accelerate. Right now it's fine, there's plenty enough to go around, but it does concern me a little bit.
I hear a lot of doom and gloom about the geopolitical situation, right, and tariffs and all of that. I see it as an advantage for our industry, right? The CHIPS Act, I think, is clear evidence of that, investing billions and billions of dollars into bringing manufacturing back to the U.S. So I know my company, TI, we're absolutely capitalizing on that. We're opening multiple new fabs right now, as I mentioned earlier. I see it as an opportunity, right? There's more jobs, that's more potential for innovation, that's more potential for students like yourselves to come into a company like TI and really take control of the future. Look forward to the new engineers coming into the company and really helping us innovate and bringing in that fresh perspective and breaking down some of the boundaries that the more OG folks like us have. So,
I remember when I first started, I've been in the industry for 30 years. I know, like a swim. And my first internship, I was wire bonding, and I literally have gone to about 15 different jobs from the bottom of the stack to the end. I don't remember, I was in the fab, most of the flash and the logic fab. There are not a lot of people in the actual factory. So when you talk about manufacturing, we're talking about the cost of building, the electricity, and absolutely, when we want to debug our products, we want to be close to it. So I get a little bit confused when we're talking about us in the sense of employability. These fabs are sources of money, but I don't know if that kind of trends with that through. And from design, yes, we consistently have design across the world, only because, again, we want to take advantage of all the great minds in the world, right? But the other part I would say is on that side of it is consumers and engineers. We were very productive during COVID. And I know as far as a director, I always have to deal with business once it's in the office versus not. So So I would say that at some point, I think the benefit of the CHIPS Act is just to recognize how important technology is to how we consume it. And if anything, the geopolitics is about our questions of what we want to solve for our society, if you will. And now we just have ways of communicating that we never did before. I can have a conversation with somebody in the middle of India for 4 hours, and then we can still resolve things. And so I see it as more of how we use technology. I'll circle back, and I remember, when I was in elementary school, we had a choir where we were sitting there talking about futuristic computers in the grocery store and in your car. I lived in a world where none of this was here. Your phone isn't brain. Your AI is an ability for you to start pulling all the information that took you so far. So the challenge is how do you take advantage of that? How do you learn it quickly and apply it to solve social large problems?
Very good. Let's see if we can wrap it up. This is again for all of you. What one piece of advice would you give to students looking to make an impact in the semiconductor industry? I think you guys have, throughout your responses, provided some ideas, but if you were to boil it down to one, because I know it's unfair, but it is what it is, what would that be?
Challenge convention. I mean, that's what I always look to students for. They don't come in with any kind of predisposition or bias on the way things should be done or what we should be doing next. And I think the longer you spend in the industry, the more you get caught up in that. This is the way that it has been done, so I want to continue to do it that way. Challenge convention. Come in, think of a better way to do it. Tell us. Show us. And I think that's the biggest thing that you can contribute.
I said find your niche and your passion early. By the way, you can also change it anytime. But if you find your passion and your niche early, when you get in industry, it makes it a lot of fun. Remember, it's called work, right? What is your objective? Minimize work as much as possible, maximize fun, right? That's my advice, right? So if you make work fun, hey, you can be there for hours on end. It's still fun, it's not work. But if it's challenging, it is work. You want to get out as quickly as possible. So find that niche, find that passion, right? Whether it's as design, software, quality, people management, project management, or UI job, whatever it is, right? Just find that very good. And if you find out that it was your passion early, and down the line you didn't like it, change. You work with a lot of companies have internal job postings that you can change around, they can switch around. Network change.
Well, that reminds me of an experience I had. So, I think first of all, communication is really important, especially when it comes to our global community. You're hearing from the other panelists say that it's imperative that we collaborate with other people in different countries. So I definitely see the soft skills, the nonverbal communication are extremely important when it comes to innovation and collaborating with other teams. The one memory I had is, so the other thing I would say is, not being afraid to try something new, not being afraid to fail. And so that experience that, I was recalling just a moment ago, it was at SpaceX at Boca Chica in South Padre. So they love using our RF instruments, especially for interference monitoring at their launch site. So they invited me to go down and help some of the engineers during the first static testing of their Starship capsule. So here I am, helping with the engineers. The engineers are, there's at least 100. We're probably about 120 feet away from the launch pad. And here we are waiting for the static testing, and I'm complaining. There was this woman next to me who was part of that same engineering group. I just assumed she was, an employee, an engineer on the team, like a test engineer, validation engineer. And here I am complaining to her, like, hey, what's taking so long? It was supposed to, this test was supposed to go on 10 minutes ago, 15 minutes ago. I don't know what's going on here. I have some other meetings or appointments I have to attend to. And she was very gracious. She was like, oh, some last minute things that we have to adjust. This is normal. Well, a few seconds later, she screams out to the crowd of 100 engineers, 10 seconds until testing. And I'm like, oh, great. I blew it. She's the director or manager of engineering. And I'm like, okay, great. and yeah, sure enough, she's looking at my shirt, and I got the Keysight logo on my shirt, and she's really taking note of that. And so, static fire went great. It was awesome. It was the first time they did this. It's like 32 Raptor engines, so it was fun. I'm walking back to their building, and I met up with the engineering manager that was using our instrument. And I told him, hey, I blew it. I was complaining to your director or manager of your team. And I described to him who it was, and he's like, wait a second. He looks it up on his phone, and the director shows me a picture, and he said, is that Kurt? I was like, yeah. He's like, dude, that's the president of SpaceX. Gwen Shotwell. I was like, what? And so the lesson there is, and you see that in that corporate culture. They're not afraid, because it turns out afterwards that their high-level executives are right there next to their engineers in the trenches, working on the prototypes and designs with them, testing it. And so that ability to overcome your fear so that you can bring yourself down. I think you mentioned, Susan, about being humble. Humility. That was a very impressive experience I had with them. So I think not being afraid, to really work on that at the beginning of your career will pay dividends later on.
So, I guess I came up with something here. So, focus on think about every day what you want to do and what you need to do, and try to spend all your time doing one of those two things. And I guarantee nobody needs to or wants to surf the phone for 3 hours. That's you'll reach the end of your life and realize I didn't spend much of my time doing what I want to do or what I need to do. And I think if you do that, you'll be happy, and you'll be happy in your job, you'll be happy in your life. So that'd be my advice.
Adulting is hard. I turned 53 this year, and I'm still trying to figure it out. So I think everyone has great advice. I think if I was going to drill in as far as new college grads, it really is about managing your own energy, right? And at some point, I think this industry has been great. Don't get me wrong, we get paid way too much money. But it's a lot of burnout. We work so much in this space, more laws about how we've done, just, that kind of thing. And so figuring out how you do that balance. And I am inspired by this generation coming in. They don't play those same roles. I'm like, why are you leaving at 5 o'clock? Everyone else is. They're like, I got things to do. And I think it's great, but at some level, you're right. Take on at least your own person, right? We are here to kind of be collectively work towards larger ambitions, company, or any type of passion you have about technology. But at the same time, don't forget about you. And if you can kind of at least navigate to this extension of what was already said, I think
Well, I wanted to say that these panelists have been amazing. So I think you probably all recognize that. So let's actually show them that we recognize.
So we heard questions from our very own Mr. Calafades. So now I'm opening the floor for any questions you have that you've been kind of holding on to since we've been very picky with questions. Let's see here.
Send them all to Jason.
Do you want to-
Hello, I'm an analog design engineer, PhD student working on analog and memory computing using Manflash. I encounter IP roadblocks every single day. Why do we, so if those IPs were accessible to me, I would get a lot of work done, but that's impossible. Why do we see such a disconnect between company research and academic research, and why don't companies invest more in academic research?
I don't necessarily see a disjunct between academic research. In fact, when I was in graduate school, Aloysius Cash, you guys know him, was a former VP and technologist at TI and ran his research group like Ed. So I would say, for for the most part, I definitely do a lot of studying, with what's going on, and our research team absolutely has more active relationships. I think A&M is a wonderful school, and, you know, Paul Gratz, for example, in computer architecture, I actually hired him at Intel when he first got out of Florida, and, for that most part, that's lined up. If you do see a disjunct, then I would say be proactive and pitch the idea. I think you could get your master's and your PhD while working full time, and your topic overlaps. Do that bridge.
I think they almost go hand in hand, you know, I mean, I spend a lot of time on campus. I do a guest lecture in the ESET department on how semiconductors work and semiconductor reliability. I see the academia kind of filling part of what the startup market also fills, right? The big companies can get bureaucratic, if you will, and get stuck in their own ideas and their own ways. And we need academia and startups to come in and challenge convention, right? Think about things differently and go and pursue new markets aggressively. And so I think we learn, right? It's a give and take. We give back to academia gives to us and brings in new talent. So I think I see it as a cyclical thing, and you know, each relies on the other.
And I just wanted to add, if you find in this conflict between academia IP and industry IP, it's just, from my perspective, finding who the right people are to make that connection. So I think that's number one. Because on the industry side, industry is not going to open up their IP and make it open source. And it's their competitive advantage, it's their secret source. However, there is interest from industry to kind of have others take a look at it. Right? And so it's, whether it's through an NDA, whether it's through other forms. Right? If you want to do work on the latest and greatest semiconductor processing, you can go through Mute, you can go through TSMC. There's ways of doing NDAs, trying to get access to that, and they do it. Right? Because there's a recognition as to what that research brings. And so it's just really finding who the right connectors are. But there is a lot of collaboration. You know, I spend a bit of my time in connecting folks, right? Actually sitting through and using some of these technologies. But it is there.
Perfect. Do we have any more questions? We have time for maybe 3 more questions, 4 more questions. Unless it's something else.
So, I'm a mechanical engineer background, I'm a grad student. And like when I was very young, you'd always think, when you think of AI, you picture a robot in the shape of a human. So, do you think, like, what do you think about the relevance of humanoid robots? Are they relevant in the present world, or do we need it in the future world? Like, what do you foresee?
So, there is a future that might. The hard problems are having the hand, no movement. I mean, there's so many muscles involved there, but I've seen some of the advancements lately, and it's staggering. So, almost everything can be done without a humanoid robot. I agree. Like self-driving cars, that'd be the dumbest thing ever to have a robot up there doing the steering wheel. So you know that's not going to happen. But and I've seen robot kitchens, and those are, yeah, you don't need a humanoid robot to do that. You have arms, and you have factories. You're never going to have humanoid robots. But the way I see it is personal companions and assistants and that caretakers and hospitals and senior centers. I mean, that is so expensive. I just had to get my parents went through that, and it's hundreds of thousands of dollars. And if you can pay $100,000 for a robot that never gets tired and always is caring and doing what's needed, that's what's going to happen. Nobody wants a refrigerator to come up and care for them. I mean, so I think there will be a place for humanoid robots, and every engineer has been dreaming about that for 50 years. So, okay. Ever since we saw the Jetsons back in the.
So we have one question over here.
Howdy, my name is Brent. Class of 26, I'm in second major. I believe it was Andrew or Jason who said that hardware is nothing without software. And as we've seen recently with ARM, you have the silicon and memory, like create risk processors. But the main issue is up until recently, there wasn't a version that's available on ARM processors, and there's still a lot of applications that are not used in that kind of architecture. So, what do you guys think will be the future of like personal computers? Because before many of us were born, it was the PowerPC, which was a RISC processor, but it eventually faded away. Then there was kind of x86 was king, but now you're seeing ARM and RISC processors making a comeback. But in the future, do you think x86 might come back again, or do you think the future is now permanently RISC, ARM, RISC, etc.?
I think it may be something that we haven't even seen yet, right? I mean, it depends on how far you want to look out. You look at quantum computing and the gains that are being made there. I mean, it could be a completely different architecture that's unlike anything we can even imagine today, frankly, right? And so, what I see happening now is with ARM, for example, it used to be 1, and then it was 2, and then it was 4, and then it was 8, and then it was 16 in a single chip, right? And so we're going to that parallel nature, but I do think that a different architecture will take over, and it may be based in a different fundamental technology that semiconductors are somehow integrated in. Like,
I would say if you study technology, I think the point between software and hardware is really the stack. What it does to how we consume it. And so, of course, you need hardware, software back and forth, but you dial back to Steve Jobs, even the whole Walkman thing, into a cell phone. It's really at that point that integration and where we consume it is different. If we have monitors for things like diagnostics on medical, like I had a continuous glucose monitor, right? That's a robot, it's a machine, it's giving information. I see what we're moving to is almost, instead of having one single entity that does everything, everything is small and it's connected. And because of that, it's the stack of how we connect, right? And so the architecture on the bottom is absolutely right that you change it, but the challenge now is how quickly we can deliver the correct solution with whatever architecture. And I agree with everyone. I've been yelling at my company and no one likes me for 2 months. You know, frequency, I don't care. I use this acronym about we're building like, you think of all the parts of computing to really translate the language into as a reference. Our CPUs are really the engine. We're building Formula One engines, plopping them into a BMW, and driving in the middle of traffic. And what's the point in that? And in the end, as consumers, all we care about the cost. We have us as engineers. I'm not to say, hey, but in my car I have these wonderful big Formula One, and that's great, but it's not really what's driving the market. So I do think there's like challenges on it, but I agree, it will be something else. It's another evolution, and it will be a different material. How do we just put, a full device, just a glove, a hand, and lotion for God's sakes? I mean, come on, this is going to be interesting how we do that.
All right, thank you so much, Ms. Graham, Mr. Shanson, Mr. Brown, Mr. Starfong, and Mr. Reyes for giving your insights on this panel, and thank you to Mr. Calafatis for moderating this panel for us. I hope you guys all learned a lot, and if you have any questions, ask them later on your own time. But thank you so much. We're going to have our panel team.